Okay, as we continue to look at trigonometry and the fundamental trigonometric identities, we're going to look in this video lecture into proving trigonometric identities. Our objective, we want to use the known trigonometric identities to prove other trig identities. All right, what do we know? Well, we pulled in this last video as well, the same stuff. We know these 8, 9, 10, 11. We know these 11 trigonometric identities. The first 8 I've called the basic ones. The last 3 here I've called are the Pythagorean ones. And we want to make use of these to prove some other identities. Now, whenever you see prove, you want to know that proving things is not easy. This is not I'll just do one step. I don't have to worry about making mistakes. Proving stuff generally takes practice. And there's probably a lot of erasing that goes on. You may find yourself going down to a dead end and thinking, what happened? It may get too complicated. And so you got to go back up again, start again. That's how proofs work. So don't think that you're going to become able to prove things quickly in a short period of time. That will not be the case. In general, when you're proving other identities, the following 3 things it helps to know. These following 3 things will help you. Number 1, you really want to have a thorough grasp of these 11 up here, because that's key to making changes to things you see and to recognizing where you might want to go with your proof. This number 2 here we talked about last time in terms of rewriting non-sines and non-cosines as sines and cosines. That's a general statement. In fact, I'll write down here, this is kind of in general. It may not always apply, but it's worth looking at to see if you can't simplify things with sines and cosines. And the following piece here, generally speaking, you want to work to change the form of the more complicated side to match that of the less complicated side. That's kind of how it works. So let's take a look. I got 3 examples here. We could do proving kind of all day because there's a whole lot you could do with this, and they all have a little different feel. You just kind of got to do them and see what works sometimes. Okay, example 1, we want to prove this identity, that the sine of x is equal to the cosine of x divided by the cotangent of x. You'll recall our definition of identity. The left side will always equal the right side no matter what x you put in there. The first thing I want to do looking at this one is I like to have my more complicated side on my left. So when I rewrite this, I'm going to rewrite the cosine of x over the cotangent of x equals the sine of x. And in general, the goal is to work with this side, and you're trying to get to this side. So I'll be leaving this side alone, and I'll be trying to work with this side. And here's one where this number 2 comes into play. We saw that in our last video lecture. In other words, we've got cosine and sine. If we could write this in its cosine and sine form, and it's not in its non-cotangent form, we might see something come out of this. So let's rewrite the cotangent. Okay, go back up to here. We know this cotangent is equal to the cosine divided by the sine. So let's rewrite the cotangent. So this would be the cosine of x divided by the cosine divided by the sine. Okay, and that equals, again, I'm trying to make the left side match up to the right side. Okay, so it's this divided by this. Well, I know that my division is the same as multiplication by the reciprocal. So I'll rewrite this as the cosine of x over 1, the numerator as a fraction, times I divide by the reciprocal, I multiply by the reciprocal of cosine of x over sine of x is sine of x over the cosine of x. And again, the right side is just kind of hanging out there because I want to try to manipulate using identities. I want to try to manipulate this left side to get to this right side. And you can see I'm already there. Okay, because I have the cosine over 1 times the sine over the cosine. Well, that's a common factor. And I wind up with the sine of x is equal to the sine of x. So I have just proven this identity, that the sine of x is equal to the cosine of x divided by the cotangent of x, by manipulating, in this case, the more complicated side using these identities. And I only had to use that one, as it turns out. I only had to use the 1 to get there. Okay, let's get a little more complicated with our second and third example. Let me get my papers together here. Okay, so our second one, let's prove this identity. That the cosine of x times the cosecant of x divided by the cotangent of x squared is equal to the tangent of x. Whew, there's a lot there, and as you might imagine with proofs, there are different ways you can do them. Okay, I'm going to choose in this case to see if I can't rewrite the left. Again, I'm going to manipulate the left side is the more complicated side. So can I do some manipulation with my identities to come up with a tangent on the right side? Okay, so first things first, I'm just going to rewrite it in my own handwriting. Cosine of x, cosecant of x, divided by the cotangent of x squared is equal to the tangent of x. So now, how can I manipulate that left side? I'm going to take a stab at this by rewriting things as sines and cosines. Okay, so I have but I'm going to leave this alone. Okay, I could rewrite this, but I'm trying to make this be a tangent. So I'm going to leave this as tangent, and that just my thinking. So the numerator would be the cosine of x times, well, the cosecant of x is equal to 1 over the sine of x. That is an identity. Cosecant is the reciprocal of sine. And then I'm going to rewrite the cotangent of x squared as the cotangent is cosine over sine. So the cotangent squared is the cosine of x squared divided by the sine of x squared. And again, I'm trying to get that to be tangent. Okay, well, obviously I have some math I can do in this numerator. And this math would be that this is going to be the cosine of x divided by the sine of x. And that's the numerator divided by the cosine squared of x, cosine of x squared, divided by the sine of x squared. And again, I'm trying to get the left side to match the right side. I keep using my identities to kind of make adjustments to see if I can't get it to, so I can cancel some things, or I can multiply and get something else, or I can use one of the Pythagorean identities, etc. Well, this is a fraction divided by a fraction. You've seen me do this several times. I don't care for that. I'd like to go ahead and multiply. So this would be the first fraction, the cosine of x divided by the sine of x, times the reciprocal of the second fraction. So it's the sine of x squared divided by the cosine of x squared. And again, I'm trying to match the tangent of x. Well, this is not bad. I see some canceling I can do. This is sine of x times sine of x, and there's a denominator of sine of x. So I can factor out this one. I can factor out one of those two sines, and the cosine in the numerator and two cosines in the denominator. I can factor that one out and one of those two. And that leaves me with the sine of x over the cosine of x. And again, I'm trying to get that equal to the tangent of x. Well, the sine of x over the cosine x is the tangent of x. And that, of course, was my goal. Okay, and there you have it. Now, again, that was the way I chose to do that one. I probably could have, if I had rewritten this as the cosine of x over the sine, if I had rewritten this as the sine of x over cosine of x and followed that down, I would have stopped right here because I would have had sine of x equals. So I would have, if I had changed this to its sine cosine form, I would have been able to stop right here. Sine of x over cosine of x equals sine of x over cosine of x. I chose to leave it, just my choice. Okay, example 3 is going to pull in, this one's tougher, for sure this one's tougher. I've been doing these for a while. I'm familiar with how to work with some of these. And so this is not one that you should be watching this for the first time and saying, oh, that was easy. I can, this is going to be kind of hard. And you probably are thinking when I'm done with this, how in the world would I have come up with that? Well, quite frankly, it's because I've done a lot of these, and I've seen a lot of these, and I've practiced a lot of these, so I have a sense of how to do it. There are different ways to do this one. I'm going to choose a particular way to do it, okay? So here we are. I'm looking at this. Secant of y squared over cotangent of y minus the tangent of y cubed equals the tangent of y. And the first thing I'm thinking is, if I change all of these to sines and cosines, I'm going to have a lot of fractions. Not happy about that. I don't like to work with fractions all the time. And so that doesn't make any sense to me. Now what I do see in here, though, is I see a secant squared, and I know there's a tangent squared in this because tangent cubed is tangent squared times tangent. So in the back of my head, and I'll draw kind of a bubble, a terrible bubble, I'm recalling the Pythagorean theorem, 1 plus tangent squared is equal to secant squared. Okay, I've kind of got that in my head because I see secants and tangents, and I see powers of secants and tangents. So when I see something like that, I'm thinking, is this possible? Can I get to a place where I get to substitute one for the other or something? Well, let's take a look. First thing I'm going to do, let's first write it down in my own handwriting. So the secant of y squared divided by the cotangent of y minus the tangent of y cubed equals the tangent of y. Well, I'm going to break a couple rules here. First off, I'm going to break a couple of generalities, I guess I should say. I'm not going to rewrite as sines and cosines, and I'm not simply going to manipulate this left side. I'm going to move this to the right, and you'll see why in just a moment. And again, there are other ways to do this. So I'm going to add the tangent of y cubed to both sides. So I have the secant of y squared over the cotangent of y equals the tangent of y plus the tangent of y cubed. Okay, let's think for a second. So, let's say here. Now, I'm going to go ahead and, again, I would like to have things as tangents and secants, and this is not a tangent. This is a cotangent. But again, I'm still thinking if I can get things as tangents and secants, I can do some stuff. So I'm going to rewrite the left side as the secant of y squared divided by 1 over the tangent of y. The cotangent is the reciprocal of the tangent, so there's a basic trig identity. And I'm going to take the right side and notice that I have a common factor of the tangent of y. So I have the tangent of, I'm going to factor that out, and I have 1 plus the secant of y. Excuse me, I don't have that. I'm too quick. I'm ahead of myself mentally and not as fast as my pencil. 1 plus the tangent of y squared. My thought up here appears down here. So this and this are identical. That's the one of the Pythagorean theorem identities. So on the left side, again, I don't like to divide by fractions, so I have the secant of y squared over 1 times, okay, well this is divided by 1 over tangent is times the tangent over 1. Looks like that, I think. And this is equal to the tangent of y, and 1 plus tangent squared y is secant squared. This is secant of y squared. Wait a second, I'm done. Left side, and I can multiply in any order I want. Tangent of y, secant of y squared. Right side, tangent of y, secant of y squared. And I've used the identities to make the left side and the right side equal. Again, that one, there are 2, 3, 4, there are different ways to doing it. I chose this method, recognizing that I can move the tangent over and come up with this. I kind of saw that. I didn't see this as quickly, but it came out. I was expecting it to go further, and it just stopped because, my goodness, I have the same thing on both sides. But that one, this one's going to take a while. This one will take some practice for sure. The key to this one, as I noted, was I saw secants and tangents and cotangent, which could be a tangent, and I saw exponents. And so I thought, okay, here's the possibility. This is the Pythagorean identity that lines up with exponents. Whereby in the other two, we'll look at the one example 2. This would be example 2. I saw all this stuff, and I elected to leave the tangent and to manipulate this side to see what came out. That way. I didn't see any. I did see a squared here, but that could be rewritten as sines and cosines. I didn't see any adding, anything like that. So I didn't see the Pythagorean here, because I don't see pluses and minuses going on. So a lot there. Just gives you some sense of a basic sense or some basic ideas on how to prove trigonometric identities.